we'll get started again. I can't make this full screen. I tried restarting. It's not going to work. So we're just going to deal with it like this. So yeah, we were talking about how the real fuels, even though they're complex mixtures, and every mixture is, can be quite different than the other, somehow when they start burning, they approximate, the kinetics approximates that they can have overall features that are similar, provided some of their key initial physical chemical properties like density, viscosity, distillation curve, Ron and Mon or cetane number are similar. And we start to then try to understand this a bit more and try to really understand what is governing the combustion of complex mixtures. So a question, again, and I always say kinetic models, combustion chemistry is not about just making models, it's about asking questions, right? So we start asking questions to ourselves, and even my own group and with my PhD students, do we really need molecules to represent a complex mixture of fuels? Do we need individual molecules? Do we need, say, 10 molecules to represent a mixture of 200 molecules? Or can we do it a different way? And again, it's not only ourselves that thought in this way. Even the group at Princeton and Dooley and Dreyer and others started to think. Rather than thinking about a mixture of many different hydrocarbons as individual molecules mixed together, can we think of them as functional groups that are actually mixed together? And very similar to this whole concept of coming back to Benson and group additivity, he said that thermochemistry is not dependent really on the molecule. It's dependent on the functional groups that are within the molecule. Again, that's an approximation. It's not a fact. And our goal as engineers are to test, is this approximation appropriate? Is it good enough? In what cases is it good? In what cases is it not good? So again, you look at a real fuel, it can have hundreds of components. But even if a molecule has hundreds of components, there's only a limited set of functional groups. And functional group is defined as some group of molecules which are present in a molecule. Let's take, for example, this very complicated mixture, something like 20 different hydrocarbons, linear alkanes, aromatics, cycloalkanes. If you look at this mixture, you can look at it as 20 individual molecules, or you can look at it as 6 different functional groups, which are just replicated or repeated across different molecules. For example, in the red, we have a group that we've talked about before, a paraffinic CH3 group. So a methyl group at the end of a hydrocarbon chain. It exists in this molecule, but it also exists in these other molecules. It exists in the aromatic alkanes, alkylated aromatics. It exists in branched hydrocarbons. It also exists in some of the cycloalkanes, yeah? So paraffinic CH3 groups. So similarly, paraffinic CH2 groups are common between different molecules. Paraffinic CH groups, these are the tertiary carbons, like we see here in the, are there any shown? There's none in this, well, there should be one here. So this should actually be a paraffinic CH group here in the black. And then olefinic groups in green, naphthenic groups are ring structures, and aromatic groups are, aromatic rings. It's just a first approximation. Can we divide up a complex molecule or a complex mixture into individual groups? Just like in group additivity, we divide an individual molecule into groups. Now we say we divide a mixture of many hydrocarbons into the groups, and these groups are common across different molecules. And it's just a hypothesis. We first ask, can we do this? And if we do this, can we start to then understand the combustion chemistry in terms of these groups rather than individual molecules? And how do you do this? Well, the simple way we test this is we take a complex mixture with many different groups, and then we make a simple mixture with the same number of groups, and we say, do they match? Yeah? So, and that's an experimental test, a kinetic test, and that's what we did. So we said, we develop an approach, and I don't say it's a real approach for modeling combustion chemistry. It's just an approach to understand, how mixtures behave. So we developed something we call MFG approach. I call it minimalist functional group approach. Minimalist in the sense that can we take one molecule or two molecules, a hypothetical molecule, with the same functional groups as a mixture with 100 or 200 different molecules, and see do they behave the same way or not. And so we call this minimalist functional group approach. It's just a way to test this hypothesis. So first, whenever we formulated surrogates, even in this previous case up here, whenever we formulated surrogates, we were taking 20 hydrocarbons or 10 hydrocarbons and we were mixing them together to match the different Peona distribution. Essentially what we were doing though is we were replicating the number of groups that were there in the real mixture. And again, groups, what Dooley and Dreyer have shown this also in jet fuels. You know, if they formulate surrogates of different complexity, as long as you match the overall functionalities, the chemical groups, you get the combustion properties fairly well. So we just took it a bit further, and we said rather than having different mixtures of 10, 15 different hydrocarbons, let's test this hypothesis unambiguously. So let's have one species, a minimum number of species, just one, maybe at most two species, to simplify the surrogate palette, and test if that one species or two species has all the functional groups in a real fuel. Can you reproduce the combustion behavior of the real fuel? And we just picked 5 representative groups. Again, the paraffinic CH3s, the paraffinic CH2s, the paraffinic CH, the naphthenic, and the aromatic. And we did this work together with Dooley at Trinity. Now the question is, how do you measure the functional groups in a real fuel? Well, you can't do this. You don't have an octane number measurement, right? Or a cetane number measurement to measure the groups. Typically what you do is you measure all the hydrocarbons, like you see here. You measure all these things that are there in the real fuel, and then you go and you count up what are all the groups. And that's a time-consuming task, but it's one way to do it. Another way to do it is what Dreyer proposed here at Princeton, is you use nuclear magnetic resonance spectroscopy, NMR, okay? NMR is a technique, proton NMR. It's like an MRI. Yeah, the same thing we use in the hospitals for magnetic resonance imaging. They use to study molecules and mixtures, and it's used in many chemistry applications. This NMR spectra, yeah, can then be used to quantify different types of functional groups. So what you do is you suscept a mixture, a fuel mixture, to a magnetic field, and then you look at the shift in the protons. As you change this magnetic field, and you get this kind of plots, it measures the concentration of protons, and the y-axis is a change in the magnetic field, and you get these different peaks. And each peak corresponds to a hydrogen unique, say, electronic environment connected to something else. So like a hydrogen that's bonded to a carbon, you know, at the edge of a chain will have a different electronic environment. Therefore, a different magnetic field will be required to observe the motion of this hydrogen particle. And so you get one shift, and in this case, the shift of a paraffinic CH3 is between like 2.04 and 2.64. So somewhere around here, the peak of a paraffinic CH would appear. This can be attached to an aromatic ring. There could be a hydrogen here. This hydrogen would have a different shift than this hydrogen, and would have a different shift than this hydrogen. So you could take a complex mixture like gasoline fuel, diesel fuel, jet fuel, and you can just get a spectral like this. Here's showing these are just 6 different gasolines, or 7 different gasolines. Sorry, there's 6. I call them phase I, phase J, phase G. There were 6 different gasolines the combustion committee was using about 6, 7 years ago to study combustion. We collected these gasolines. We measured the NMR spectra. And then we get based on the area of each peak, you calculate the total concentration of each type of group. So it's like a fingerprint then. And you see every fuel has its own functional group fingerprint. So this fuel phase A has much more of things like paraffinic and C alpha CH2s, secondaries and primaries, whereas this fuel, phase G and phase F, they tend to have a lot more aromatics, yeah, and olefinic groups. And like this, you start to count up the different groups. Okay, it's not something you're going to use in industry. Industry doesn't have access to NMRs sitting in the back of the office. But again, researchers have access to NMRs. We start to use this approach first just to understand, does it make sense to characterize a fuel by its functional groups? And this technique is then used to calculate all the different functional groups that are there in a real fuel. So that's step one, measure the functional groups in a real fuel. Second step, measure or make some hypothetical mixture which matches the functional groups in the real fuel. So we make these different surrogates, okay? And we make surrogates of different complexity. So a group at Livermore has proposed surrogates with like 4 species, toluene, heptane, isooctane, PRF means heptane, isooctane, plus 2-pentene to represent 387 gasoline. Nayak et al., who worked for Chemkin, he made a 5-component surrogate. Ahmed et al., at KAUST, he made a 6-component surrogate for some gasolines. So in our approach, we say we don't want to add species to make the surrogate. We want to remove species. We want 1 component or 1 species or 2 species at most to match the overall functional group distribution. And we found that, okay, for this fuel, phase A and phase C, they actually have very similar functional group distribution within like 5% of each other. And this one molecule, 2,4-dimethylpentane, approximates very well the different functional groups in these linear alkanes. Similarly, phase F and phase G, you could take 3-methylpentane, mix it with indane for phase F at the right proportions. Phase G, 3-methylpentane with tetralin. Phase J, and heptane with toluene. So we try to reduce completely the number of surrogates and the number of components and just say 1 or 2 components with the same functional groups. And then we make the surrogate. So the surrogate is simply a mixture of 1 or 2 components. And then again, we put that in an NMR, or we calculate by hand the functional groups. And we see, okay, you can match the functional groups. So we can match fairly well. There's errors. Okay, it's not perfect. This is an engineering approach. So we're about 3% off in the paraffinic CH3s. We neglected completely the aromatic because it was only there at 0.5% in the overall mixture of phase A. So we just said, forget about it. Yeah, phase G, you see the errors are a bit larger, maybe 7% on the paraffinic CH3s, 5% on naphthenic, but we get the aromatics closer. Okay, and we're going to see. We're a bit off in the exact functional groups, but does it really matter or not? And like this, we did this for different fuels. And then you go and you do experiments. So we didn't build models and test them. We bought these molecules, or we synthesized them, and we make the surrogate, and then we do experiments with the real fuel and the surrogate, and we see, do the experiments match each other or they don't match each other? So we do different experiments like jet-stirred reactor experiments. And you see here, jet-stirred reactor experiments. We measure formaldehyde at different temperatures, and we measure the mole fraction. We do this for the real fuel, phase I. We do this for the surrogate. And we also did it for a more complex mixture. And we see pretty good replications, yeah? They pretty much overlap with each other. Similarly, we take the real fuel and the gasoline, and we put them in an ignition quality tester. This is not a kinetically controlled device. It's a IQT used for measuring cetane number. But we say even something like a global combustion property, like the ignition of a flame, ignition of a spray, can be, within 0.2 milliseconds, one component surrogate matching the functional groups of a real fuel gives you virtually the same ignition delay time. And this is again some more JSR measurements. JSR predictions for OH profiles. We do this also for all the different surrogates. We measured them, again, in IQTs and rapid compression machines at KAUST. And we started to notice there's some commonality. Even 1 component or 2 components matching the functional group gives you pretty much, within 5–10% error, the overall combustion characteristics of a real fuel. Okay? Now, is this to say that you're going to get the species formation exactly correct? Probably not. Yeah? Are you going to get the soot formation exactly right? We don't know. There's more tests have to be done. But it goes to show, at least, the functional groups appear to be the governing phenomena, okay, or governing the kinetic phenomena, many kinetic phenomena in combustion systems. And with this knowledge, can you simplify your kinetic models? Can you make it easier now to model real fuels? Before this, we said, okay, if functional groups from these experiments that we have done, these experiments which are trying to understand the governing phenomena of combustion kinetics, if functional groups appear to be the important step, okay, to understanding the phenomena, can we use these functional groups to simply train a machine learning model? Yeah? And you can. So we just said, okay, rather than having complicated kinetic models to predict things like octane numbers and cetane numbers and soot formation and flame speeds, if we know the functional groups in the real fuel, why not just use that as an input to some nonlinear parameterized model, either a neural network or some other time. And again, it's not a fancy study to do. It's just a simple experiment. We measured NMR spectra, now not for 5 fuels. We measured it for 300 different fuels. Yeah? And then we also have cetane numbers and octane numbers for these fuels. And then we just simply train machine learning models. So again, I take now these different functional groups, yeah? And I say these are the inputs to my model. We train a neural network, take these inputs, match the cetane number or the octane numbers. First, we started with about 100 different mixtures, and now we're up to about 500 different mixtures. We use 6 different functional groups. The problem is functional group is not sufficient, because if you want to predict things like ignition of a spray, it's not only the functional groups, it's the carbon number. The volatility matters because the spray has to evaporate and burn. So we use the functional groups and the molecular weight. And we make it a bit more elegant as well. There's something called a branching index, because this functional group approach, this is 1, 2, 3, 4, 5. This is so these are all 3 different isomers of N-heptane, okay, of heptane, sorry. So this is N-heptane. This is 2-methyl-hexane. They're all isomers of heptane. And this is 3-methyl-hexane. The octane number, who knows the octane number of N-heptane? 0. By definition, the octane number of N-heptane is 0. Okay? Then you have a molecule like 2-methylhexane. Well, the RON is about, I'm guessing, okay, I forget exactly, but it's around maybe 40. And the RON of this guy is around 30, okay? Now, the functional groups of these 3, this molecule is only CH3s and CH2s. Well, this guy has CH3s, CH2s, but also CH. And this molecule also has CH3, CH2, and CH. These 2 molecules have the exact same functional groups and the same number of functional groups. But if you see, the octane numbers are different. So actually, the first approximation saying only functional groups is enough is actually wrong. Because if you take this methyl branch, it's 1 functional group. All you do is move it away, move it over 1 position from 2 to 3, the octane number changes. So the kinetic phenomena is governed by the location of the branches as well. So that made it a bit more complicated. Okay? But you can determine locations of branches as well using NMR. And we have algorithms to do this now. So we call this 8th term a branching index. The branching index is a number that tells us the location of different branches whenever you have branching on an aromatic, on a cycloalkane, on a linear alkane. So again, and these are things you can measure and then you can calculate. So that's why we have 6 functional groups, molecular weight, and branching index. And now we start training different machine learning models. Nothing fancy about that. It's pretty simple machine learning in the end. If you have your data and you have your inputs, you just follow your basic, the correct approach for machine learning so you don't overtrain your models. And it's nothing fancy in that sense. And we start to see, okay? We've developed models for about 300 different fuels for RON and MON, 500 fuels for cetane. Again, we use NMR to measure the functional groups, and then you get very good correlations, okay? And because it's simply the functional groups, we know we're the governing phenomena, governing the kinetic phenomena. So if you have this as an input to your machine learning model, you can predict very complicated combustion kinetic phenomena like cetane numbers, octane numbers. And now people are doing this for flame speeds and other things as well. As long as you have the database, you can train your models. Okay, and but again, machine learning models don't help us answer complex questions. They're just good for fitting and sometimes for industry to use. But again, we want to come back to the point. We want to understand very complicated phenomena, and we want to build some more representative physics-based models, which can be extrapolated. Machine learning model will always be confined to the training set and the range of data that you have for your training set. Whereas if you have good fundamental models, you could put them in CFD codes and make predictions. So there is an approach developed in, let me see if I can hide this, in Stanford by Professor Hai Wang called HiChem. Anybody heard of HiChem? Okay. HiChem approach. It's a very elegant approach to dealing with real fuel combustion chemistry. And it came out around 2018. And we're going to cover that. We're actually going to even listen to a lecture for about 20 minutes from Professor Hai Wang about this approach, because I think it's important for you guys to understand really the state of the art and also how it's been taken further. So in 2008 to 18, he again looked back at the work done here at Princeton. He saw, okay, the work done by Dooley and Dreyer, that you have real fuels. Real fuels are mixtures. They break down to intermediates. Those intermediates break down to small species, and they govern the kinetic phenomena. And Hai Wang said, okay, real fuels are these complex mixtures. They're reacting with oxygen. He said the first step of that reaction is something we call oxidative pyrolysis. And he says this pyrolysis, or this oxidative pyrolysis, yeah, is a relatively fast phenomenon. And you can build, again, in any kinetics, if something is fast, like a quasi, remember in the beginning we talked about quasi-steady state approximations, right? So if something is fast, we can make we can lump the steps together and say one kinetic phenomena governs it, just like in quasi-steady state approximation. If a radical is short-lived, we can make an assumption that this kinetic phenomena for the production of the radical and the consumption of the radical can be lumped together in one step. So he's saying something similar here. He's saying that the fuel undergoes a rapid oxidative pyrolysis to some intermediates, like Dooley and Dreyer had also postulated. And then those intermediates undergo further oxidation to small hydrocarbons, which make radicals. And he said this second step is the rate-limiting phenomena, or the governing phenomena of your system. And based on, again, this conceptual phenomenological understanding, he started to build a model, okay? And we'll see how the model is built and how he tested that the model works. So, and then I'm going to talk a bit more about how we took his approach, and we can even take it a bit further. So let's watch that now. I'm going to...
So far, everything I've talked about is about explore with you something of a flame. What does flame do when you not multi, but big hydrogen here? As an example, what I'm plotting here is the structure of an adiabatic flame. Let me explain slowly, okay? I have the temperature profile, I have the cold boundary, and this is a adiabatic flame. What you see here is a major, is the fuel, okay, seen. This is the you form energy. You look at the structure of this flame, you find that where flame is intense as marked by chemiluminescence of electronic inside of the CH. This is where the blue flame is. It's somewhere here. Your temperature is already very close to the adiabatic flame temperature, the final flame temperature. But look at this. This large field, NB2 cyclohexene, is long gone, finished, disappeared, before the flow reaches the flame. So where did the fuel go? It went to ethylene, it went to hydrogen, it went to methane, and it went to propane. Now, this is not new. If you go back to look at the Norbert Peters paper back in the 1990s, this is all being told in the context of how do you even determine the Lewis number for this type of flame. Nevertheless, so what will happen is that in this temperature region, before the flame, temperatures around 12 to 1400 Kelvin, the fuel already undergo pyrolysis. It's disappearing on you. Replaced by what? Replaced by ethylene, methane, propane, hydrogen, and some other minor species. Okay? And if I replace N-butyl cyclohexane by other large hydrocarbon compounds, whatever this may be, they also crack. They may crack to different type of products, but they always dissociate. And as a matter of fact, if you have the feed fuels with that larger molecular weight into the flame, I can assure you this flame from fundamental flame dynamics point of view, the flame will never be stable because you run thermal diffusive instability there. So nature actually did us a great favor there. That it doesn't matter what you burn, large hydrocarbon, they will dissociate into a bunch of intermediates that have similar molecular weight as a molecular oxygen. And that's why you don't run into thermal diffusive instability problem. Okay, so to summarize and quantify, for flames, you get this 100 microsecond window over temperature range of around 1050 to 1450 Kelvin. And this is when the fuel you feed into the flame got converted entirely to small hydrocarbon species. They decompose to a set of small species, and this is how flame works. This is one set of data. I always use it because it's a beautiful set of data, again, done by my colleague Ron Hansen. Okay. If you look at the mole fraction of species, shock tube oxidation of N-dotted king, C12H26, in oxygen, diluted in argon with equivalence ratio of unity. Okay, so this is diluted mixture, and so you can follow the species well. If you're interested in a legacy combustion property, ignition, that's about 700 microsecond. And within this 700 microsecond, you look at this problem, you say, fuel is gone in the first 20 microsecond, 95% of fuel is gone, because keeping in mind, this is log scale, the time axis. Replaced by what did fuel? Ethylene. You see that? Ethylene goes up very quickly, levels off, and for the next 700 microsecond, you're doing not the oxidation of the fuel, but you're doing oxidation of the fuel pyrolytic product. Already, but never burn large fuel directly or never oxidize large fuel directly. You oxidize the fragments of its dissociation product. So that's the key point. How general is this observation? So summarize, we'll have pyrolysis first, oxidation second. Oxidation takes much longer, and they are, of course, rate limiting. That's a key characteristics of burning large hydrocarbon real fuel components. Okay, oxidation process takes 700 microseconds, and oxidation of ethylene is rate limiting. How general is it? And this is a set of data published some years ago by Ken Brzezinski from UIC. Rather than plotting the mole fraction of species in a time domain, Ken fixed the time of reaction to about 2 milliseconds in the shock tube. Then look at concentration of the fuel, which is here, he used N-decane, and oxygen as a function of temperature. And different symbols here represent different equivalence ratio, from fuel lean, stoichiometric, fuel rich, to pure power pyrolysis, where equivalence ratio is infinity. Let me break this chart down. If I draw a line here around the 1200 Kelvin, did you notice? N-dotted king is all gone by 1200 Kelvin. Not much oxygen has been consumed. So where did the N-dotted king go? It can only go to pyrolytic product. In other words, whether you do pyrolysis or oxidation, fuel always decompose first. And notice that at a different equivalence ratio from lean to pure pyrolysis condition with infinite equivalence ratio, you do not see variation in those symbols in the mole fraction of the fuel. In other words, the presence of oxygen almost do not ever impact the pyrolysis condition. And that's great. If that is the reason that we can start to decouple the process of fuel pyrolysis from subsequent oxidation of pyrolytic product by molecular oxygen. Okay, so those are the physics again, indicating measurements. Field pyrolysis first, fragment oxidation next, and field pyrolysis is not affected by oxygen concentration. Why is it? Look at the pyrolysis, and this is entirely thermodynamic driven. So this is a complicated chart, and I wanted to jump in this for 1 minute. Bear with me. If I look at the Gibbs free energy of reaction starting with a field, I just generically call it C11H22. I have some enthalpy of formation, therefore enthalpy of combustion defined for this field. I ask that if I expose this field to 1300 Kelvin, 10 bar pressure, thermodynamically, as far as chemical equilibrium is concerned, what would it evolve to? Well, if I run this pyrolysis using, say, Pantera equilibrium code, what you're going to find is the final product of the pyrolytic reaction is actually carbon and hydrogen. If you will, this will be soot and hydrogen. All right. And what is the driving force? Enthalpy-wise, you see enthalpy continue to increase. That is, this reaction is endothermic. You need heat in order to get it going. The other way to look at this is, because of this endothermicity under adiabatic condition, the more you dissociate a field, the lower the temperature, therefore the slower the kinetics is going to be. So enthalpy is not a driving force. Enthalpy works against dissociating the product. What drives this process is, in fact, entropy. Entropy goes larger as you break down a hydrocarbon field into smaller components, mostly involving hydrogen. Hydrogen wants to go free, and this is why field likes to crack itself. And keep in mind, entropy goes up, and if I plot negative temperature times entropy, this should go down. You sum up enthalpy and entropy term, you get a Gibbs free energy. And it is because of entropy process driving the reaction with always negative Gibbs free energy to go to final equilibrium product. Yet because enthalpy is working against you kinetically, the system gets stuck somewhere here. Somewhere here is where you find dissociation products that you see in previous charts. Those are involving hydrogen, methane, ethylene, some C3, C4 species. So this is the thermodynamics of this problem. Okay. And thermodynamics of this problem is such, it doesn't matter what you start, thermodynamics will clean things up for you, leading to only a smaller number of components you shall consider or you need to consider. So if you start with 1,000 components, upon this thermodynamic filtering, you get only a few small species, and there's a small C1 to C4 species. That's a key point. And to prove this point, system always gets stuck in C1 to C4 hydrocarbons. I'll take N.Eke. I pyrolyze it at 1400 Kelvin adiabatically at a 1 bar pressure. Because of endothermicity of dissociation, the temperature drop as N.Eke concentration drop, replaced by ethylene, predominant, hydrogen, propane, 1-butene, some ethane, methane, and so on. Keeping in mind, this is log axis. So if you just consider this group of pyrolytic product, you'll find you're recovering 98, 99% of carbon mass. So again, the point is, pyrolytic products are trapped first in the local metastable potential energy basin, and they are stuck there, and for 500 microseconds, they do not kinetically dissociating all the way to hydrogen plus solid carbon. And this is the soup, in fact, we burn. And the time scale for this to happen is about 100 microseconds. Recall that in the flame, I talk about this 100 microsecond time scale. Okay. All right, so I'm going to jump through this. It's not important. So given all this understanding, what do we do? I want to make sure that I don't run too long. Don't want to take too much of your time for a Saturday morning.
It is okay. Please go ahead.
I'm sorry?
It's okay. Please go ahead.
Okay. All right. Thank you. So to summarizing everything that I said, what are we seeing here? All the evidence, thermodynamic, chemical kinetic, statistical, and so on, all indicating that if I have a large hydrocarbon field, whether it's a single component or multi-component real field, I call this field generically a C sub m, H sub n. Under certain temperature, radical presence, and molecular oxygen presence. The initial reaction process, if you heat it, whether it's in the flame front or through other means of heat transfer, raising the temperature, what you're going to get out is a set of intermediates. I denote this intermediates as X sub I. Okay, and this process is fast, very fast. They're not really limiting, and it's not even dependent on oxygen concentration, and doesn't even depend on whether you are in an oxidative condition or in a pyrolytic condition. Then these intermediates or pyrolytic products, this is C1 to C4 intermediates, ethylene and so on, their oxidation in molecular oxygen finally producing combustion product. That's rate limiting, that's slow. So if you look at this physical understanding, how would I put a model together? I would jump through all of the large set of reactions describing how few get to those intermediates, okay? And it's unimportant how long it takes, because you remember for this shock tube problem I said earlier, ignition delay time is 700 microseconds, dissociation time of the fuel is 20 microseconds. If I'm way off, I'm off by a factor of 2 in fuel pyrolytically, rather than 20 microseconds of dissociation time, if it's 10 microseconds, the total error in the overall ignition delay time prediction is simply a few percent, okay? So the point here is, this first part, you can simplify it. The second part, you have to treat it very carefully. What it translates into is the following. Again, before I get to the next point, so far everything I talk about is theory and some limited experiments. So let me now give you some real field measurements to show that this assumption is valid and is correct. My colleague Tom Bowman did a field pyrolysis, field oxidation experiment, in his turbulent flow reactor. The reaction time is a little longer because we need to lower the temperature to see the species well. 20 milliseconds, 1 bar, 1140 Kelvin with 300 ppm of fuel. And what you find is that for 3 different jet fuels of different composition, the intermediate species that are produced from the initial fuel decomposition stay more or less the same, dominated by ethylene, some methane, propane, benzene, toluene, butadiene, ethylene, acetylene, and there's about half a dozen, 6 to 8. The rest you add together is relatively small, and this relative as far as the combustion goes doesn't contribute to heat release. You can simply put the rest back into the field if you want to model it. Right. The point is that all this fuel have over 1,000 fuel components, cover 4 or 5 different organic hydrocarbon classes. But once you pyrolyze it through this first step, as in a pyrolytic process is a lens, you're actually focusing the reaction process down to production of a very few components, about 6 to 8 you in fact need to consider. And that simplification is also the necessary and sufficient condition for real liquid fuels don't vary in their combustion property, as I discussed earlier. And that's also explain why this is so. If all what I said is true, and you believe what I say, then we just needed to develop some very simplified reaction models. Taking the fuel called a CmH sub n, this can be a jet fuel, this can be a gasoline fuel. And all what you have to do is conserve mass, carbon and hydrogen mass. And you can massage the lump the reaction process into something that looks like what I'm showing here. All the Greek letters marked in red are properties, are parameter values that we need to determine. Where the blue letter, English letter, ED and BD, EA, and so on, are dependent variables. These values depend on the Greek letters, the alpha, the beta, the lambda, the chi, and so on. So if you ask me, why did I cast the model in this way? It's because algebraically it's the simplest, and each of these Greek letters are independent variables, and they have physical significance. For example, the parameter alpha is the number of H atom produced in the CC fission reaction per fuel molecule. And beta has its meaning. Gamma is the ratio of methane the methane yield per fuel molecule. Okay, and this is in addition to H abstraction by method. Lambda 3, lambda 4, those lambda parameters are the ratio of higher alkenes, propane, and butene. This butene can be 1 butene, can be 2 butene, can be isobutene, and you can expand to it. The ratio to ethylene. Ethylene is always one of the dominant products. Chi is the ratio of benzene to benzene plus toluene, and their ranges bound, and so that you can only choose values between the value given by the blockage. The dependent variable ED, EA, and so on can be determined essentially from the fuel stoichiometric coefficient, C, M, and N, plus the various Greek letters. So the way how you cast this model is nothing more but to A, to make your algebra simple, B, those property of stoichiometric coefficient values, in fact, can be determined by the experiment. And I'll illustrate that. So all this is done you have to describe as intermediates. As I discussed earlier, there's a way to write simple algebra conserving the mass, and there's a hydrogen for the intermediates and ethylene and so on, okay? And one of the things we don't recognize when we write detailed reaction mechanism is a majority of those reactions you see in 100,000 reaction mechanisms do nothing but try to conserve mass. So in other words, if the reactions are not rate limiting, what you write the reactions are for is only for conserving elements and conserving mass. So in a way, the best one way to say this is you're using integration to implicitly conserve mass. But since your carbon to hydrogen ratio in the field, if that is known, carbon to hydrogen ratio is known. In fact, your dissociation products must be correlated to each other. For example, if you look at the ethylene yield per any kind of fuel molecule called C11H22, plot against the methane yield, they are highly correlated, okay? And those are the few bands that depends on benzene tolerance ratio. And you can show this, those bands constrain methane yield and ethylene yield very tightly, in fact. And those are some measurements down in Raun's shock tube for several different fuels. And also, if you look at the aromatic yield, they're also bound, very bound. There is a very small parameter space or variable space. You can choose those stoichiometric coefficients. All right. All that said, how did we do this? Real fuel, pyrolytic process, producing those intermediates. This is one step along the reaction model. It's anchored on elemental conservation and kinetic parameters, including those stoichiometric parameters, alpha, beta, gamma, will have to be derived from experiments. Once you have these pyrolytic products, their reactions are rate limiting, and you need to now switch to detailed model. And this detailed model can be reduced to about 30 species. And for that reason, the final HiChem model is about 30 species for a real fuel. You never need to have anything more than that. So we use experimentally measure the species profile to inverse the problem, determine the kinetic model parameter. And those are what I showed you earlier. We have 6 stoichiometric coefficients. And for radicals of H methyl OOH, O2H, O2, 6 of them plus 1 more. So we have a 7 rate constant, 6 stoichiometric coefficients to determine from experiments. Okay. We do not use flame data or global combustion properties to fix those parameters. We only measure the species concentration to determine the model parameter. Then we test and validate the resulting model against the global combustion properties, flames, and shock tube. All right. So the problem is casted essentially into 13 independent variables that are to be determined by fundamental experiments. Okay. And we use a foundation fuel chemistry model. We use CMAP2, but you can use anything, as a matter of fact. It's not that important. And I'll skip through this to show that some of you might ask, how do I know those coefficients, the stoichiometric coefficients, are constants, independent of temperature and pressure? So therefore, the model as written, as a constants, they are general. And we have a detailed argument given here through very simple steady state analysis. And I will not go through, I'll jump through that. For those who are interested in this problem, you can read some of those papers, which I'll give you the list at the end. The key point is, by throwing away perhaps thousands of reactions, just to write it simply, I have, for example, N dot king dissociated into hydrogen, methyl, ethylene, and so on. And each of these values is basically what I showed you earlier, related to alpha, beta, gamma, the Greeks. And then you have a secondary reaction just with all being a series of radicals, and with their stoichiometric coefficients simply derived from detailed model. Okay, but now from few all the way to the small species are described by essentially 2 long the reaction step. You can reproduce flame speed extremely well, and you can reproduce ignition delay time without tuning anything. Right, so that shows that many of these detailed models so many reactions are completely unnecessary. They are doing nothing more but to conserve mass, okay, through a long list of chemical reactions. So we do speciation from flow reactant and shock tube to develop a model. We then use global combustion properties to test the model. What kind of data? My colleague Ron Hansen measures the ethylene and methane species concentration as a function of time over a range of conditions. In this case, would it be for different fuels and a similar temperature pressure condition? And this is the kind of a curve we fit. By fitting this curve, we can back out those parameters, the HiChem kinetic model parameters. Those are the Greek letter parameters and rate constants. And you can do this over a wide range of temperature for yield of methane and ethylene and over different reaction time. Okay, it is this type of measurements we do. And you can also do this in oxidative condition. The experiments I showed you earlier are simple pyrolytic experiment. And you can do this in the oxidation experiment. Remember, with or without oxygen, stoichiometric or infinite equivalence ratio or pyrolytic condition, you don't see that much effect in species that are produced. And this is yield of ethylene again, and not much difference. Okay, so the lines are the model and symbols are experiment. The other type of experiment we rely on, okay, is the flow reactor. We can map out more species, but stretch the reaction over a longer period by employing lower temperature. So there's a constant temperature flow reactor experiment. This is the field for JP8, ethylene, hydrogen, propene, and 1-butene. It is a propene and a 1-butene measurement allow us to determine the ratio of this species, their yield to ethylene. Those are the lambda properties, if you recall. We have benzene and toluene. So the inverse of this problem is it allows us to fully determine those kinetic model, high-K model parameters. And there are some more examples showing the measurements in sharp tube, and they are open symbol model prediction. Okay. Now we have high-K model. Trust me, 13 parameters, a lot to fit. So we need to have a quite wide range of experiments, but those are not too bad. Typically, for a given field, 2 weeks of experiments are good enough. And then you have all the model parameter with the high-K formulation. The next question is, do some sharp tube ignition, validate it. Turns out that most of the species measurements were made at 12 bar. You're then actually going to ask the question, can the model be extrapolated to higher pressure and to wider temperature range? The answer is definitely yes. Remember, those Greek letter parameters are not dependent on temperature, not dependent on pressure either. So as we expect, when you derive the model parameter at around 12 bar, apply this to 50 and 30 bar high pressure, you actually predict things very well. And now when you get to the last set of experiment, you see you have a solid line and a dashed line, single side experiment. The reason you have 2 lines is because when you get to that condition, air-like condition, you start to see NTC behavior. So once we add NTC chemistry, I'll talk briefly later, you reproduce the data much better. Long story short, wide range of multi-component real fields, wide range of thermodynamic conditions, high-K works as well as those surrogate models, if not better. Volcanic populace measure the flame speed at 1 bar and extinction strain rate in non-premix counterflow. And we're going to see that model, this is a prediction. We did not tune the model parameter against any of this experiment. It does very well. If you're asking why it does so well, it's actually a foregone conclusion for reasons I already discussed earlier. It's a multi-component, so there's no reason to expect it won't work for flame speed. Okay. Volcan also measure high pressure flame speed in his spherical bump. The blue symbols with error bars are the measurements, and the red lines are high-K model prediction. Okay, without a fitting, you see that the model works well under that condition. So the next question you're going to ask is, how much uncertainty do we have in the model? Or the other way to look at this is, how good is the measurement uncertainty for species profile? Ethylene. In Ron's sharp tube, Ron is always very proud that he has the most accurate measurement for species in a sharp tube, and his measurement uncertainty is 20%. With 20% uncertainty, how does that uncertainty in the ethylene species measurement propagate through high-K model parameter and into model prediction for global combustion property? This is what a symbol represents. Nothing on flame speed, somewhat on ignition delay time. But trust me, that kind of uncertainty is not that large as far as any of the reaction model is concerned. And then if you push me further, say how good it really is your overall high-K model. Well, actually, the current uncertainty of high-K model can be pretty large, but that uncertainty is not in a high-K lambda reaction part. That uncertainty is in the foundation field chemistry, that's C1 to C4 hydrocarbon part. Why is it? That's rate limiting. All the sensitivity goes to small hydrocarbon oxidation reactions or rate constants, not on the large species. Okay. All right, I'm coming pretty close to it. Thank you for bear with me. Some of you may ask, well,
So we'll just briefly summarize what he says, right? So again, last 4 days we've been talking about very detailed chemistry, complicated reactions, all of it's important, and then Hayek Wang says none of it matters. Yeah? None of it matters because many combustion phenomena are governed by the rapid decomposition of the fuel, to form some intermediates, and again, those intermediates burn, and they govern the global combustion phenomena. And then his high chem approach actually stands for, not his name, high, okay? It's hybrid chemistry. Hybrid chemistry. That's what it stands for, high chem, okay? Hybrid chemistry in the sense that you hybrid, is it showing there? Oh, it crashed, huh? Sorry. I don't have to make, I shouldn't make it full screen, I forgot. Hybrid chemistry in that you have a hybrid reaction step, so you have a lumped step at the beginning, and then you have a detailed oxidation mechanism. So you're taking a lumped fuel chemistry model with a detailed small species chemistry model, and this, therefore called hybrid chemistry. Now this way of lumping, it's not new, okay? There's a group by Professor Ranzi in Milano, okay? He's retired now, but actually he's been talking about this since the early 1990s, while groups in Livermore, in Princeton, like Westbrook and Dreyer, were building detailed kinetic models in the 80s and 90s. Ranzi always said, none of it matters, lump everything together, yeah? Lump the pyrolysis reactions together and just have a detailed model. And that was his philosophy since the early 90s. He was one guy in the combustion community who stuck to this. The group in Milano sticks to that philosophy. Do these types of lumping approaches because, yeah, many kinetic phenomena can be lumped together, especially pyrolysis reactions, and you can predict then complicated phenomena. So the group is called CREC modeling group, okay, in Milano. And if you're interested, you can learn more about their modeling and their studies. They've done many over the years. So, you know, Professor Haiwang follows a similar approach. He takes some lumping steps and then a detailed oxidation model. How does he determine the lumped reactions? Well, he has an equation that says a fuel molecule with some number of carbon atoms and hydrogen atoms. He doesn't care about the structure, yeah, of these. He just says this is going to break down to many intermediates, ethylene, propene, butene, benzene, toluene, methyl, and H radical. Why methyl and H? Well, methyl and H are the radicals that govern the combustion phenomena. So you need to fix the parameters. And these parameters, alpha, beta, gamma, and so on, are something like stoichiometric coefficients. Coefficients which tell us in the reaction equation the amount of moles, which then becomes the amount of mass of each of these species. So and how does he determine these coefficients? Did anybody get it? So do some experiment. So his colleague, Professor Hansen and Professor Bowman, they take the fuel, they pyrolyze it, and they do some experiments, and then they measure the concentrations of ethylene, propene, butene, and then he simply fits the curves, yeah, by prescribing what the function is, or what the coefficient is, to get the best fitting against the experiments. And okay, the approach works, and then he showed many examples, right? Many examples of how this works to predict flame speeds, to predict ignition delay times. And we asked ourselves, why does it work? Well, it works because he has constrained your reaction model against, you know, experiments which predict the intermediate pool of species. And then if you have that right, and then you put that into a model to predict something like ignition and flame speed or extinction, it works because you got the amounts, concentrations of all those intermediates correct from the fuel, and then you have a good model to predict how these intermediates break down and form things like H, OH, CH3, which lead to the combustion phenomena that are manifested. Now, you know, our team, we like this approach. It works really well, but one thing I wondered about, okay, with the postdoc was, can we follow the same approach, but we don't need experiments to figure out these variables, right? Because this approach still requires that you go get a jet fuel or a gasoline fuel or a diesel fuel, you give it to Professor Bowman, who has a flow reactor, or Professor Hansen, who has a shock tube, and they have to do the experiments. And then what happens if you come up with a new fuel, yeah? How are you going to get these parameters and build the model again? So we thought, can we come up with an approach which builds the entire model without doing any experiments? And if you have any new field that comes about, can you build the model, let's say, automatically without worrying about it? And can you make it predictive in the sense that the model is then developed without experiments on the actual fuel to build the model? And the approach we use is we come back to the functional groups. So we said, OK, previously we saw the functional groups are able to predict the real fuel combustion of a complex molecule. These functional groups were able to train a machine learning model. Can we use these functional groups to train the HiChem model? Yeah, the parameters for the HiChem model. So we'll talk about this once we take a last 10, 15-minute break. And then when you come back, we'll talk about how you can build the model functional groups for a real fuel. Okay?